Hello everyone and welcome to week 11 of Poll 361. This week we're going to learn how to test our hypotheses and understand what it means when we say something is statistically significant. So in this lecture we're going to review what it means to test our hypotheses. We're going to talk about the difference between type 1 and type 2 errors. I'm also going to get you a little familiar with the terminology we use when we're talking about testing our hypotheses, so the difference between null and alternative hypotheses. And then we're going to start getting into some statistical tests that we can use. So for this week's lecture, we're going to talk about comparing sample means to hypothesized population means. And there's two different ways that we can do this depending on the sample size. If we have large samples, we can use z-scores to test the difference of means. So that's going to be building on a lot of material from last week. Alternatively, if we have small sample sizes, and generally this is samples under 30 observations, we will use t-scores to compare sample means to population means. And then finally, we're going to end the lecture with understanding confidence intervals, how to calculate them and interpret them. And all of this is going to be the foundation that you will use to model your relationships in your research papers, and then we will start using stata in the class to test data and determine if our variables are related. So with all that being said, let's go ahead and get started. In this lecture, we're going to discuss two kinds of inferential activities. The first is hypothesis testing. This is the act of confirming or disconfirming empirical statements about data. We use probability theory to determine whether we can confirm or reject a hypothesis. And in this lecture, we're specifically going to test hypotheses with regards to the sample means and comparing those to hypothesized population means. Sometimes you don't have a hypothesis for what the population mean should be, and in those cases you use point and interval estimation. So with this method, we estimate unknown population parameters from samples with confidence intervals. And this leads us to estimations such as we're 95% confident that somewhere between 46 and 49% of Americans support the job Joe Biden is doing as president. So this is a very common method used for public opinion polling when the true population parameter is unknown. Now, before we really get into the details, it's important to understand that there are actually two types of hypotheses. The first is the null hypothesis. This is typically denoted as HO or H naught. And the null hypothesis states that there is no relationship between the data being studied. And because we can never really know the true population values, we can never actually definitively confirm our hypotheses. Scientifically, the only statement we can make is demonstrating that our data is rejecting the null hypothesis or rejecting the idea that there is no relationship. On the other hand, we have alternative hypotheses, and this is what you have the most experience with in this class. These are the hypotheses that we hope will be validated by our data. They state directionality, an effect, and relationship between two variables. So when we reject the null hypothesis, we say that our data favors the alternative hypothesis. This can be denoted in a variety of ways, HA, H1, H2. I generally prefer listing your hypotheses with H1 and H2, but it is up to you. Let's run through some examples to make sure you understand the difference between a null hypothesis and an alternative hypothesis. So the alternative hypothesis, we'll begin with this one, the one that you should be most familiar with, stating directionality, being plausible, all of those characteristics of hypotheses. For this one, we have Democrats will be more likely to favor the current president than Republicans. Well, yes, that makes sense. The current president is a Democrat, so we should expect Democrats to be more favorable towards the president. Now remember, the null hypothesis is always going to state that there's not going to be a relationship between the independent variable and the dependent variable. So very simply, the null hypothesis here is that there will be no difference in support for the president between Democrats or Republicans. This is the thing that we want to reject. We want to prove this to be false, and that is how we find evidence for our hypothesis. Let's try another example. Let's take this alternative hypothesis. Women are more likely to support reproductive rights policies. Again, the null hypothesis states that there should be no relationship. So very simply, the null hypothesis here would simply state there will be no difference in support for reproductive policies between men or women. Let's see if you can figure out the null hypothesis on your own with this final example. Here, the hypothesis is that states with higher populations will have more small businesses. So really think about what the independent variable is here and what is the dependent variable. You can go ahead and pause the video for a moment and think this over and try to figure out the null hypothesis. Now, what's key here is that population size is the independent variable, and this statement is suggesting that as population increases, so will the number of small businesses. So since the key independent variable here is population size, that means that our null hypothesis would state population size will have no impact on the number of small businesses. So just remember, the null hypothesis is the thing that you are trying to reject. If you can at least prove that it is highly improbable that these two variables are not related, then you have evidence for your hypothesis. And one last thing we have to discuss are types of errors that occur in hypothesis testing. There are type 1 errors and type 2 errors. A type 1 error happens when you claim that there is a relationship in the data when there actually isn't. In other words, you're rejecting the null hypothesis when you shouldn't. Type 2 errors, on the other hand, occur when you claim there is no effect in the data when there actually is. In other words, you're confirming the null hypothesis when you actually shouldn't. And just as a note before we move any further, when we're testing hypotheses, we're focusing and calculating the probability of making a type 1 error. This is denoted by alpha. Tests of statistical significance calculate this probability. When researchers claim that the results are in fact statistically significant, they are claiming that the null hypothesis is rejected with a specified probability of making a type 1 error. Now, another way to think about the difference between type 1 errors and type 2 errors is illustrated here in this pretty ridiculous photo. The point of the matter is that a type 1 error can be thought about as a false positive result, whereas a type 2 error is a false negative result. And when it comes to statistical inference, we're essentially calculating the probability that measure the likelihood of making a type 1 error. In other words, how confident are we that we have not made a false positive correlation between our variables? And when our critical values fall within a specified rejection zone, we are rejecting the idea that we have made a false positive assessment. Now, I know all of this probably sounds a little confusing. We're going to have a lot of examples, but I want you to think back to the very first week of class, and we talked about the characteristics of good science, the characteristics of good empirical research, and one of the things we discussed was how making absolutist statements like X will always affect Y in this very specific way. Well, that leaves no room for doubt, and that essentially becomes an untestable statement. So as social scientists, it's not our job to use statistics to state that there is, in fact, an undeniable relationship between these two variables. Rather, we have to remain objective. We have to leave open the possibility that another sample collected by another researcher in another point in time might provide different results than ours. So our objective is to simply report our level of confidence via probabilities that two or more variables are in fact related. Now, when we get into hypothesis testing, there's a varying degree of levels of confidence that we can use. These are referred to as levels of statistical significance. And the most common ones are 0.05, which means you're 95% confident in your results. or a 5% chance that you are wrong, an alpha level of 0.01, which means you are 99% confident in your results, or there's a 1% chance that you've made a type 1 error. And then the most critical level, the hardest one to prove, 0.001, which means there's a 99.9% chance that you're right, or a 0.01% chance that you've made a type 1 error. Now, in statistics, all of these different thresholds, 0.05, 0.01, 0.001, we typically denote these as P. And P stands for the probability of making a type 1 error. In other words, saying that there is a relationship between the data when there really isn't. So we always want P to be very, very low. The smaller that P is, there's a smaller probability that your inference is wrong or that the null hypothesis is actually true. So very, very small P values are good. They indicate that there's a very small probability that you are wrong. So consider the research statement. In our study, Democrats were significantly more likely to evaluate Joe Biden positively. Our data suggests that party affiliation significantly predicts presidential approval at the 0.05 level. And this is an example of the way that I'd like you to report the relationship between your variables in your research paper, but let's break this down a little bit more and try to understand what this statement is actually conveying. With the 0.05 level here, it's saying that there's the probability of making a type 1 error or a false positive is 0.05. That's very, very small. There's a very small probability that the inference is wrong. Another way of thinking about this is that the inverse of a 5% chance of being wrong means that there is a 95% chance that we are right. So in other words, we have 95% confidence in our results. And this is why understanding the normal distribution and standard deviations and z-scores is so important. They will guide everything that we continue to do in this course. Based upon the mathematical principles and assumptions of the normal distribution, we know that 68% of observations are within one standard deviation above and below the mean. And when we branch out to 2 standard deviations, we know that 95% of observations should be within this range, assuming that the data is in fact normally distributed. So when we collect a sample, determine its mean, and if we find that value to be in the tail of the distribution, then we have really serious concerns over whether or not this hypothesized population parameter, mu, we have really significant concerns over whether or not that's correct, because we know that the probability of falling in the tails is very, very low. So when you're testing a hypothesis of a sample mean against a hypothesized population parameter like this, and the sample z-score falls in this rejection zone, well, we're rejecting the idea that this population parameter is accurate, because we know it is so highly improbable that an observation would fall in this tail in the first place. Now what you see here is a one-tailed test where we only have one rejection zone and it's to the left of the mean. We can also perform two-tailed tests, which means we might not know if, we might not know if the value is below the mean or above the mean, and I'll share more information on that later. But for now, let's just walk through an example and try to make sense of, this rejection zone and alpha and hypothesis testing and all of that. So imagine a friend tells you that most Americans are no longer moderate, and instead they tend to be much more conservative. Now you disagree with your friend, and you say, I don't think that's true. I hypothesize that Americans are instead more liberal. So in order to test this hypothesis, we will rely on our trusted 7-point ordinal political ideology scale that ranges from strong liberal to strong conservative. We have worked with this measure a lot in this course. So as you know, the way that we code responses, if we were to go out and collect public opinion responses and ask people to report their political ideology, we know we have to assign numerical values to each of these categories. And in this case, strong liberal is coded as 1, and as we increase in ideology all the way to strong conservative, we end up with a value of 7. So this measure ranges from 1 to 7. Now I want you to think about this. If your friend is correct that Americans tend to be more conservative, what would the mean ideology score have to be for that statement to be true? And remember, moderate is coded as 4, strong liberal as 1, and strong conservative as 8. So if we had an average of 2, that would mean that on average, people were selecting strong liberal or liberal. That would suggest that our sample is really, really liberal. If our sample average was 6.5, right? That would suggest that a lot of people were selecting conservative or strong conservative. And if our sample average was around 4, that would suggest that almost everybody selected moderate. So here what we're trying to do is ascertain the hypothesized value of the true population. And if the statement is true that most Americans tend to be conservative, well, what value would the average have to at least be? You can think about that for a moment and go ahead and pause and think about how the categories are coded, and then we'll return. So hopefully you were able to guess that if your friend's statement was true, the average ideology score would have to be at least 5, because 5 corresponds with leaning conservative. And so that is what we're going to try to disprove. So you can see that denoted by the null hypothesis here, that mu, or the population parameter, must be greater than or equal to 5. This is what we want to reject. We want to show that that mean ideology score is much lower, because that corresponds with our hypothesis, more Americans being liberal. So here we have the alternative hypothesis. We're arguing that mu is actually less than 5. This is what we want to confirm. So in this example, we're going to run through how to test this hypothesis with a 95% confidence level. Here are the steps that we're going to run through. So I would be sure to pay careful attention here and take notes. These are the steps that you need to follow when you're comparing a sample mean to a hypothesized population mean. So step 1, we're going to choose a suitable level for alpha. How confident do we want to be in our results? Do we want to be 95% confident? Do we want to be 99% confident? Do we want to be 99.9% confident? And again, this is all up to the researcher. You know, there's a big difference between being 50% confident in something versus, 95% confident. So that level is really up to you, but the point of the matter is that people aren't going to really buy your argument if you say, oh no, these variables are related. I'm about 72% confident they're related, but it's all up to you, the level of alpha that you choose in your own research. So after you've done that, step 2, you determine the z-score for your specified alpha. We refer to this as a critical value of z. Step 3, we calculate the observed z from the differences of the means. So observed z is simply your sample mean minus the hypothesized population mean, and then we divide that by the standard error. And then step 4, we compare the absolute value of our observed z-score to the critical value of z, which is the threshold for our rejection zone. And if the absolute value of our observed z is greater than the critical value, then you can confidently reject the null hypothesis. So that all probably sounds very terrifying. Let's go ahead and do an example with a one-tailed test. So suppose that we determined that our sample size mean was 4.27. In other words, y bar equals 4.27. So this is already really good news for our hypothesis. Our friend thinks that Americans are more conservative. Based upon the measurement of the variable, we know that that would have to be the average mean would have to be 5 or more. We already see that our sample mean is less than 5, but is it low enough that we can be confident in our results? That's what we're going to try to figure out in this example. So let's just pretend that the sample size, or n, was 920. Let's say we calculated the variance, and then we calculated the standard deviation, and we determined that sigma hat was 1.47. Again, sigma hat is the sample standard deviation, and we want to set alpha to 0.05. Okay, remember that this means that we want to be 95% confident in our estimation, or we are satisfied with a 5% chance of being wrong. Well, how do we do this? We've talked a lot about alpha. How the hell do we figure it out and measure it and get the correct value? So I want you to think about alpha as a rejection zone. And we already talked a little bit about this. When we compare our sample mean to the population mean, and show that the sample is significantly different, way off in the tails, then we reject the null hypothesis. We reject the idea that the population parameter we've hypothesized is correct. So when alpha is set to 0.05 and we demonstrate that an observed sample value lies inside this blue rejection zone, we are 95% confident in our results. In other words, if we can show that our sample statistic falls in the tails, outside of where 95% of observations should be, then we reject the hypothesized population parameter in favor of our sample. And again, it's because the probability of our sample falling in the tails is so low that we reject the idea of what that population parameter specification is. Now think back to, I know that's that might be a little confusing still, but I promise with the example, it's going to make a lot more sense. But the first thing that we need to do is we need to establish this threshold, this cutoff point, this rejection zone, and come up with a value that's going to show us where 95% of observations should be. So think back to the z-score lecture. How can we identify the 5% or 0.05 rejection zone? Well, here we use our trusty z-scores. As you remember from last week, we discussed how these scores tell us what percentage of observations exist between the mean and a specified point of interest. So we're kind of doing some reverse engineering here. We want to figure out, instead of figuring out the point from z to the mean, we want to figure out the point of z beyond into the tails to where we get to this 5% rejection zone. So this is the table that we worked with mostly last week. Here is the second part, or I guess the bottom half of that page, blown up in a little bit more detail. And what we need to do here is find the z-score that correlates with the 5% rejection zone. So let me show you this graphic before we proceed. We know that 50% of observations are to the right of the mean when the data is normally distributed. Now what we want to do is we want to find the z-score that's going to show us where 45% of observations are from the mean to the left. And all we want to be left with is this 5% rejection zone. So all we need to do is find the z-score that correlates with 0.4500. So we go back to our table. We search the table for something close to 0.4500, and here we go. We've got this row, 1.6, and we take that all the way to the fourth and the fifth column. Here we've got 0.4495 and 0.4505. We want to be at least 95% confident, so we're going to go with this z-score here, 1.65. And the reason that we do this is because if we were to go with the 1.64 z-score here of and the shaded region here would be 0.4495, when we added that up with the other side of the distribution, really we'd only be about 94.95% accurate, as opposed to going with the 1.65 z-score, which is going to technically be at the 95.05 threshold. But the specifics really aren't important. I have a cheat sheet later in the lecture that shows you which z-score you use depending on your alpha level and whether or not you're doing a one-tailed or a two-tailed test. So don't really worry about that right now. But I'm showing you the Z table to illustrate what exactly it is that we're doing. So we've identified our critical Z-score of 1.65, and that shows us that 5% of observations are below that point, below that Z-score, and 95% of observations are to the right of that Z-score. So we want to show that our sample mean falls in this rejection zone, so we can reject the idea that the population parameter is 5. So 1.65 is our critical value. Now we need to calculate our observed Z. And remember, the calculation for this is simply our sample mean minus the hypothesized population mean divided by the standard error. And we've talked a little bit about the standard error before, but I don't expect anyone to have memorized that equation. The standard error is simply the standard deviation divided by the square root of n. So our standard deviation, as we see up here, is 1.47. We're going to divide that by the square root of the sample size, so the square root of 920. That gives us, the square root of 920 is 30.3. So we take our standard deviation, 1.47, divide that by 30.3, and then we determine our standard error, which is 0.048. Now that we have our standard error, we can continue on calculating our observed Z. So we take our sample mean, 4.27, we subtract that by 5, because that's our hypothesized population mean, and then we divide that by the standard error that we just calculated, 0.048. And when we do all of that math, we end up with an observed Z of negative 15.21. So this is our observed Z statistic. The last thing that we have to do is take the absolute value of that observed Z statistic from our sample data, 15.21, and we have to compare that to the critical value of the Z with the 95% confidence level. Remember, that critical value of Z was 1.65. And remember, this is part of the final step. If the observed Z is greater than or equal to critical Z, then we reject the null hypothesis. We reject the idea that that true population parameter is actually 5. So ask yourselves, is 15.21 greater than 1.65? It absolutely is. So therefore, the probability that we have made a type 1 error is extremely small. And according to our sample, Americans do not appear to lean conservative. In fact, our data suggests that they are very far from that. Just to show you a graphical representation of what we've just done, we have hypothesized that the population mean is 5, or it's at least 5. And we're arguing that it's actually way under that. We think that the population mean is equal to 4 or 3 or 2. We definitely think it's less than 5. So it's somewhere over here to the left of the mean. That's what we're hypothesizing. We created our rejection zone with a 95% confidence interval. So we used a Z-score of 1.65 to determine where 95% of observations should be if the population mean were in fact 5. We calculated our observed Z, and that had a statistic of negative 15.21. So if we were to graph that, it would be all the way over here, really, really, really far away from the mean, more than 15 standard deviations away from the hypothesized mean. So again, the probability of, collecting a sample and making sure that we don't have bias in the way that we've collected our data, the fact that we have observed a sample statistic so far away, so improbable from what should happen if the mean really were 5, this means that we have a lot of confidence in our results, and more specifically, there's a very, very small probability that we have made a type 1 error. So I hope that those examples made sense. In the second part of the lecture, I'm going to go over two-tailed tests. I'll talk briefly about t-distributions and how to conduct this same type of test, but in the case that you have far less observations, generally observations less than 30. And then I'm also going to talk a little bit about confidence intervals, how to construct those, and how to interpret them. So I'm going to go ahead and end this video so you can pause and take a little bit of a break. If you're still a little fuzzy about anything that was covered in this video, I strongly recommend that you go to the point that you started to get a little bit confused. Maybe rewatch that before proceeding, because again, the rest of the lecture is going to continue to discuss or build upon these foundational concepts discussed in this lecture. At any rate, as always, if you have any questions, make sure to post those in the discussion board, and go ahead and end this video, and part 2 will be next.